Hello, I'm Amanda Lewandowski, and I'm also here with Isaac Caskey and Tyler Hall. And today we're going to be talking about the IoT Chassis Controller Senior Design Project. A little background on the project is that Terex Utilities builds and sells digger derrick, auger drills, and aerial device trucks. And Terex provides technical support and assistance for these vehicles, whether or not they're 2 miles away or 2,000 miles away. And usually the trucks are pretty far away, so they have to try and provide support over the phone, which can be very difficult. It's pretty difficult to obtain diagnostic data over the phone and very expensive to try and fly out a technician to the truck, and so we were tasked with providing a solution to send the truck's CAN data over to the support location via Wi-Fi or cell service. And we were tasked with providing as close to real time as information as possible for the CAN messages, along with two-way communication so the technician can interact with the truck.
For our system, we chose the Raspberry Pi computer instead of a microcontroller, mainly due to its processing power and out-of-the-box Wi-Fi support. The Raspberry Pi also supports open-source Python modules such as Python CAN, which let us easily interface with our chosen CAN hardware modules. For our cloud service, the AWS IoT Core was chosen for its speed, along with its lower cost compared to services like Microsoft's Azure. Packaging of vehicle CAN messages was necessary for communication over AWS. Our project packages 50 CAN messages into every AWS message, then unpacks them on the other end. With our two-way communication sending both the vehicle's messages and user-generated messages to each other, the CAN ID filter program was developed to prevent a message loop condition. This program interacts with the technician and allows them to input the ID of the messages they want to send to the truck before they send them. An option was also provided to filter only the last two characters of the CAN ID, known as the source address. Our system also supports both the OBD2 protocol used in smaller trucks and the J1939 protocol used in larger ones. It also supports 250K and 500K baud rates for maximum compatibility with different manufacturers. Finally, the device used in the truck can be powered directly off of the vehicle's own diagnostic port. No need for an external power supply. Next, we'll show you guys a video of the setup and a quick demo.
So we'll start with setting up the truck end. A J1939 pass-through connector was used to connect the truck to the Raspberry Pi in the truck. The Raspberry Pi would get power from this cable as well as CAN data, which it would stream over a AWS IoT core. The touchscreen connected to the Raspberry Pi provides a means for the user to connect to a network and enter the password if necessary. The Raspberry Pi on this end is set up to start transmitting data as soon as Wi-Fi is connected. Now we'll look at the setup on the diagnostics end, where the truck is currently streaming data to. So you hit connect on the Raspberry Pi, then you run this .exe file. This will allow you to choose the truck whose data you want to read. We'll just enter 1 and then click connect. Now it's hitting connect. Now it's connecting to that truck. Now entering the source address, which is the last two characters of the CAN ID, will allow two-way communication between the diagnostics end and the truck. Click filter. Here's a little video of the setup. So there's the Raspberry Pi. There's a CAN bus module. And there's a PCAN to USB cable, which is running up to the computer. And on the computer is some software that Terex themselves developed, allowing them to communicate with the controller in the truck. Here is some live CAN data streaming from the truck. Next will be a live demo.
Ready?
Yep.